Hello, welcome to the course Electronic Systems Design. Today we are going to discuss the color coding of resistors. So as we know, we have multiple passive components which we use in electronic system design. Most of the time we work with resistors, capacitors and inductors. These are mostly used components on the circuits. So we have this, for example, resistance we take. The resistance value, how do we know the value of a resistor? We have multiple values of resistor available in the market which we can use. So first of all, we do not get resistance for all the values whatever we want. There are only set of values which are available in open market which we can buy and use in our system. So these are the only values available to us which we can use. So while doing our design, that time also we should take care what are the values typically available in the market which we can use. Once we know all these values, when we buy these resistances, these components from the market, these components are not written any values on top of these components in actually on those components. So if we buy, let's say 100 resistances, maybe the box is written a value like 100 kilo ohm, but if we take an individual resistance, it's not written anywhere on that resistance or anywhere that this is a 100 kilo ohm resistance. So we do some sort of color coding to know what is the value of that resistance. So there are certain color coded rings we make on the resistances. From them we can know what is the actual value of this resistance. We can calculate the value of resistance based on these color codes or color bands. So this is the process typically followed for all the resistances. This is there for multiple reasons. For example, we may not have that much space on the component itself to write the exact number on the resistance itself. So we put some sort of color codes which we can see and calculate how much is the resistance of that component. So this is called the color coding of resistances. So let's see what this is. So today we are discussing color codes of resistances. So manufacturers typically use a color band system known as the resistor color codes. So all these manufacturers, whoever manufacture these resistances, they use a particular code to signify that this is the resistance value of that component. This is known as the resistor color codes. These codes give only the resistance value of the component. There is no other parameters mentioned by this color coding system. For example, one very important parameter is the power. How much power dissipation this actual component can handle. So this rating is not generally specified using these color systems, that we know from the manufacturer itself. When we buy these components from the manufacturer, that time we specify we need X amount of power dissipation which the component can handle. In that power rating, we want this value of resistance. So that resistance value we can calculate from the color codes, but the actual power which the component can handle, that we have to know from the manufacturer itself directly. So that number is typically given in the data sheet, which is a complete document specifying all the parameters of the components. So those numbers are generally not available by color code system. So we have the power rating is not indicated in the resistor color code. And must be determined by experience using the physical size of the resistor. So the power rating is actually not indicated by the color code system and must be determined by experience. For example, if the size of the resistor is large, it means it can handle much more power because this has more area or more volume to dissipate that amount of heat. However, if the same resistance value is available in a small form factor, the size of the resistor is small, then it can handle very small amount of power. Otherwise, if the same amount of power is dissipated, that resistance is going to burn out because of heat dissipation. So it's a kind of general rule, if the physical size of the resistor is more, it means it can handle higher power compared to its smaller counterparts. So this power rating is generally by the experience or by the size of resistor. Next thing is, because we buy these resistances in bulk and there is a machine which is making all these resistors, there is a tolerance of these resistances. Generally, the resistance are available like 2%, 5%, 10% tolerance. It means if we buy a 100 kilo ohm resistance, not actually 100, it can have a certain variation from 10% plus 10% to minus 10%. So according to these tolerance levels, we have two types of color codings. One is we use the 4 color bands in one resistors, and if we need a very accurate resistance value, then we go for a 5 band system where we place 5 rings of 5 different color codes to specify the values. So we have two types of color codings. For resistors with plus minus 5% or plus minus 10% tolerance, color code consists of 4 color bands. And for resistance with 1% or plus minus 2% tolerance, the color code consists of 5 color bands. So we have two types of resistor components available in the market. One can have 4 color bands and the other one can have 5 color bands. So these color bands specify the amount, the value of the resistance which we have. So let's see the these resistance values from color codes. So as we have seen, the resistor nominal value is encoded by the color code. In powers of 10 notation. So we can see how to determine the nominal value and tolerance from color codes. So here we want to see how do we determine the value of resistance from the color codes. So for example, we have this component which is a typical resistor, and here we can see we have 4 color codes, this 1, 2, 3, and this is the 4th ring. This is 1, this is 2, this is 3, and this is 4. So these are the 4 rings which are available on this component. This is a typical resistance. So, how do we determine the value of this resistance from these color codes? So, here if we see this first band, here we have this first band, this specifies the first significant bit digit. This second band specifies the second significant digit. And this third band specifies the multiplier. And this fourth band this specifies the tolerance. So these are the meanings of these multiple bands. Now how to determine the value of this resistance? We have the first significant digit here, we have then the second significant digit here, which comes, this first digit come from this color code, second digit come from this color code, and the third digit is the multiplier, which is 10 to power something. This is the total value which is in ohms. So this third parameter comes from the third band, which comes as a multiplier from the color band, and the fourth value is the tolerance, which is percentage variation if we buy this component. So how much is the percentage change we can expect in the actual value? So this is the percentage tolerance. So this is the formula actually we calculate from the resistor, where we have 4 bands here. First band is the first significant digit, for example 1. Second band is the second significant digit, for example 0. So here it becomes 1 0 multiply by 10 to power multiplier. This is the third parameter which comes from the third band, which can be a number, and 10 to power, let us say 2. So let us say multiplier is 2, so 10 to power 2. So 1 0 means 10 into 10 to power 2, it means 10 into 100, which is 1000. So this resistance value is 1000 ohm. Then it is multiplied by some tolerance level. This fourth band is the tolerance. For example, it is saying 10%. It means this 1 kilo ohm can be 10% higher or 10% lower compared at the nominal value. Nominal value is 1000. So 10% higher it can be, or 10% lower it can be. So this is the tolerance percentage. How do we calculate the number from this color code? That we can see in the next slide here. So how do we know which color corresponds to which number? So for this we have something called the resistance color code table, which is shown something like this. So here in this table we have particular color and what that color represents in terms of digits. So for example, black, if the ring is black, it means the value of the digit is 0. If the color ring is of brown color, then the digit is 1. If the ring is red, then digit is 2, and so on. So based on this color table, we can determine what is the actual value of digit we have to put in the formula which we just saw in the last slide. In that formula there are empty spaces. Those empty spaces we need to put this digit. This digit comes from the color ring or the color code which we put on the resistance. So let's take some example how to determine these values. So this is an example. Determine the nominal resistance value and the tolerance the resistance shown below. So here we have this resistance and this has these color codes. Now how to determine the actual value of this component from that table which we just saw in the last slide. Those color codes represent certain digit in the actual number, and how do we calculate the actual value of this resistance. So here we have the first band, this is brown, and the brown color from the last table, can see this represent digit 1. The next band is black, and the black represent 0 from the table. The third band is red, which represent the number 2, and the fourth band is the gold, which represent the number 5. So according to the formula, we have 2 spaces to fill in the digit, and then we have 10 to power multiplier, this much is the ohm value, and then we have plus minus this fourth parameter in terms of percentage. So these 4 values we need to put, that we put from these numbers. For example, this brown, first band is brown, so first parameter, first empty space we need to fill is by 1. This second band is band, so it means it comes out 0 here. The third band is red, which is 2, so the parameter is filled by digit 2, and the fourth band is gold, which is 5. So we put the fifth, this parameter as 5 in the tolerance level. So now we see the nominal value of this comes out to be 10 multiplied by 10 to power 2 ohm. This is 1000 ohm, and the tolerance is 5%. So here we see we have this color coded component. We see all these 4 bands. First is brown, black, red and gold. Accordingly, we put the values as 1, 0, 2 and 5. In the formula, we fill it out. We put 1 as the first digit, second is 0, then 10 to power 2. This is the nominal value of this resistance, which comes out to be 1000 ohm. So if the color code is like this, it means it's a 1000 ohm resistance. The fourth band signifies how much is the tolerance in the manufacturing. So if it's a kind of lousy made resistor, then the tolerance limit can be higher, for example 10%. If it's a very precisely controlled process by which we make these resistor, then the tolerance level may be 1 or 2%. So depending upon what is the manufacturing technology used for this component, we can have tolerance higher and lower based on that. So this tolerance, for example, this component shows a 5% tolerance. It can be 5% higher or 5% lower. So we can take another example to calculate one more resistor. So in this we determine the nominal value and tolerance. Then we also calculate the minimum value of resistor. And what is maximum value of resistor? How do we calculate these values? So here we have this component as an example, and we want to calculate how much is the nominal and tolerance values, and what is the maximum value this resistance can have, and what is the minimum value of resistance this can have. So here again we see we have these 4 bands. The first band is yellow. This yellow color represents 4 from the color table. Second band is violet. This represents the digit 7. The third band is orange, which represents the number 3, and the tolerance band is again gold, which represents digit 5. So if we calculate the value of this resistance, this is the first digit, second digit, multiply by 10 to power the third multiplier, this much ohm, and then we have plus minus fourth space, which is the tolerance value. So if we put the numbers from above, we have 4, then 7, then the 10 to power multiplier, which is 3, and then tolerance is 5%. So now we calculate. So the resistor nominal value will be equal to 47 multiplied by 10 to power 3 ohm. This comes out to be 47 kilo ohm. And the tolerance is plus minus 5%. So here in these two examples, we have calculate the nominal value of resistor and the tolerance. So in this example, for example, we have a nominal value of 47 kilo ohm. So this is the value 47 kilo ohm, which is the nominal value. However, depending upon the manufacturing of this component, the resistance value can be up and down. It can be higher than nominal value or lower than nominal value. It depends on the tolerance, how much tolerance the component has. If we manufacture these components by a very precise process, the tolerance will be smaller. If it's a lousy process, then this tolerance value can be 5% or even higher, 10%. We want a precise number, for example nominal number. We want to buy a 47 kilo ohm resistor from the market, but it can always change based on the tolerance. So the next step is now what is the maximum value it can have, this 47 kilo ohm, or what is the minimum value it can have, this 47 kilo ohm, that we want to calculate based on the tolerance. So we have the minimum resistance value So for this, we will multiply the nominal value by the tolerance and subtract this from the nominal value. So the minimum value is equal to nominal value minus nominal value into tolerance. Our example, it comes out 47 kilo ohm is the nominal value minus 47 kilo ohm into 0.05, which is the tolerance. So it comes out 47 kilo ohm minus 2.35 or so kilo ohm. So the minimum value of resistance can be 44.65 kilo ohm. So if 47 kilo ohm resistance, when we put this on the actual circuit, it can come out to be minimum 44.65 kilo ohm. It may not be exactly 47, but within the tolerance value of 44.65 kilo ohm. Similarly, we can calculate the maximum value of resistance. So in this, we multiply the norm value by the tolerance, and then add this to the nominal value. So the maximum value we can have norm value plus nominal value into tolerance. So this comes out to be 47 kilo ohm plus 47 kilo ohm into tolerance, which is 0.05. So this is 47 kilo ohm plus 2.35 kilo ohm, and comes out to be 49.35 kilo ohm. So these are the maximum and minimum value of resistance, which is 47 kilo ohm norm value, but because of the tolerance, the minimum value and maximum value can be 44.65 and 49.35 kilo ohm respectively. So from this we can see the tolerance is higher, it means the value which we actually get, it can be very much higher or very much lower compared to the norm value. So what is the significance of this? For example, when we make circuit, we generally do it on the some software which are CAD softwares. In this software, we design a circuit assuming that we will use a 47 kilo ohm resistor from the market. So, according to this 47 kilo ohm, we are getting some results in CAD software, which is a computer software. This calculate precisely the output based on the actual 47 kilo ohm. It assumes that the resistance we will use is exactly at 47 kilo ohm. So, based on the CAD software, we get some output. However, when we want to fabricate this circuit on the actual hardware, we buy this 47 kilo ohm resistance from market. This comes up with a tolerance which is 5%. So, now if we see, this 47 kilo ohm is no more a 47 kilo ohm, it can be a 44.65 kilo ohm or it can be a 49.35 kilo ohm. So, based on this variation, our actual output can be different than what we designed in the software, because the software assumed the resistance will be exactly 47 kilo ohm. However, in practice there are certain tolerance always present in all the resistances. Whatever we buy from the market or whatever we manufacture, that has certain tolerance, higher or smaller, it does not matter, but all the physical components, they have certain amount of tolerance. Nothing is exactly precise at that point. So, there are tolerance always there, and based on that, our system which we actually going to fabricate, that will have different output compared to what we simulate in the computers or software. So, in this example we see this 47 kilo ohm can be as high as 49 or can be as low as 44, which is a very large window. We have 5% of tolerance. However, for making the systems very precise or in advanced system, we cannot afford this much tolerance in our components. So, we go for high end manufacturing where we can have a smaller tolerance. We can pay the price for those costly manufacturing process, but those components have the tighter tolerance limit. For that, we need to have different color coding system. Here we are confined with 4 color codes. However, for the precise tolerance, we may go for 5 color codes. We can see in the next slide. So, we can have 5 bands. So, we can go for 5 band resistors. So, for resistors, with only plus minus 1% or plus minus 2% tolerance, color code consists of 5 bands. So, for example, we have this component. So, here we can see we have 5 bands instead of 4 bands. Based on these 5 bands, now we are going to calculate what is the value of this resistive components. So, here instead of first 2 digit as a significant digit, now we have 3 bands. It means 3 digits to specify the significant digit, so that we can specify up to 2 place of decimal what is the actual value of this resistor. So instead of using only 2 bands, now we use 3 bands for the significant digits, and the rest 2 bands are similar to the 4-digit 4 color code register. The last one is the tolerance, and before that we have multiplier. So the only difference is, instead of using first 2 rings as a significant digit, we have first 3 bands to specify the significant digit. So we can calculate the using the same formula or the similar formula. So this first band is the first significant digit, first significant digit. This second band is the second significant digit. The third band is third significant digit. The fourth one the fourth band is a multiplier, and this fifth band is the tolerance. And the formula is very similar to this. So now we have first digit, second digit, third digit, which comes from this first ring, the second ring, the third ring, and then we have 10 to power multiplier, which comes out from this fourth band, and the tolerances. This is the fourth, this is the fifth parameter, which comes from the tolerance, which is in percentage. So here we see we have these 5 bands. Instead of the first 2 bands which was there in the 4 color code system, now we have 3 bands dedicated for the numbers which are the first band, second band and third band, and the rest 2 bands are very similar to the 4 ring system, the multiplier and the tolerance. So rest things are exactly like this, which we calculated in the last slide. For example, brown number represents 2 or 1, so that number we put here. So for example, 100 multiplied by 10 to power whatever 2, and then the tolerance. So we can calculate the nominal value and the min max value of this component. So these are the 2 systems which we broadly follow for naming the color, naming the components and specifying the value of that resistor. Now we see what are these resistance and how do we put them on the actual system when we make in the electronic system. So we go to something called the mounting technology. This says how do we put these resistance on the system. So here in this figure we see this is the resistance value, this is a simple resistor, and how do we put this on the system? We make something called PCB, This green color thing is called PCB or printed circuit board. In this we have multiple layers coming through, which are used for connection of different components. And here, for example, if we see this is a resistor. Now if we see carefully, this resistance has these two metal pins coming out. What we do, we drill a hole in the PCB here, and this pin goes through the PCB and we solder it on both the ends. We remove extra length of pin which is there. So we see this is the arm of this resistor which is going through the PCB. So we see this, while putting this resistance on the PCB, we drill the hole into the PCB and we put the component so that the pin goes through the hole, and then we solder it. So this type of technology is called the pin through holes or the PTH technology, or these components are PTH components, the pin through hole components. So we have these pin through hole. PTH components. The problem with this type of technology, where we have this PTH resistance, the problem is these lead wires which are coming out from this component. The actual resistance is this brown color thing which is there in this bead. To connect this resistance to the external circuit, we use these two arms, these metallic wire comes out. These bond wires actually contributes to the parasitic inductance and capacitance. Whatever these wires, these may be longer or shorter, but these extra wires, they contribute to the parasitic inductance which is undesired, because we have not accounted for in our actual design. So these bond wires contribute parasitic inductance. And the other problem with this kind of design is, for multiple signals, PCB actually may have mechanical problems. So this is the problem if we have so many resistance we want to put on a PCB. So for each resistance we need to dig two holes in the PCB, assuming we have 100 components together. So we have to drill the 200 holes in the PCB. So actually while drilling the hole, the mechanical strength of the PCB goes down. So this is the problem if we have multiple PCBs, multiple components to put together. However, the good thing about mounting these PTH component is, these PTH components are generally bigger in size, so they can handle more power dissipation compared to the other kind of technology. So we have here the good thermal reliability. So the good thing is we have here good thermal reliability. So this is the PTH type mounting technology. Next we talk about something called surface mount technology. So in this actually we have resistance not like a cylindrical component coming out two lead wires. We have just a small piece of ceramic which is the resistance, and on the both side of this block we have these two ends are coated with solder, and this is acting as a connection to this resistance. And when do we put on the PCB, it look like this is the PCB, and we need not to drill the hole in the PCB, we just need to put two metallic pads on the PCB where we put this surface mount resistor, and then we heat up so that this is connected to the PCB. So here we have multiple advantage of this surface mount devices, or we call these SMDs, surface mount devices. So for example, one is they are very small in size compared to our PTH devices. They are light in weight. We need not to have drilling the holes in the PCB. So mechanical strength is good for the PCB. They can be mounted on both the sides. So if we are not drilling hole, we can design the circuit such a way half of the circuit is on the one side and half of the circuit is on the other side of PCB, and we can mount on both the sides, and they can have a very high switching speed because they are very small, so the parasitic effects are very small. The only problem with SMD components, they cannot handle as much heat as those PTH component can have. That is because the size of these components are very small compared to those PTH components. So we have certain advantage and disadvantage which we can list out. They are smaller in size, the higher density, no PTH needed, so good mechanical strength, can be mounted both sides, and higher speed. So these are the advantages of SMD components. However, we have some drawbacks. So there is thermal problems. Manual design is difficult. They are very hard to handle manually. and high precision PCB needed. So we saw two types of manufacturing technology and two types of components. One is through PTH, where we dig the hole and we connect the bond wire to the PCB. There we saw these extra bond wires create so many problems. First is the parasitic effect, and because of these parasitics, the speed of the circuit is limited because the parasitic effects reduce the switching speed. So in the surface mount, we have smaller components which we can connect on the both side of PCBs, and because of the small size, they do not offer that much parasitic effect. So our circuit can achieve higher speeds. The drawback is the thermal problems. They cannot handle that much of heat. So but in today's world, we need to have more and more components together to make different and very complex circuits. So in recent time, we are switching more and more to surface mount technology, and SMD components we are preferring over the traditional PTH components. So now we see the resistance and different capacitances. They also are available in surface mount form factor. So we have surface mount inductors and capacitors. So here we see this is a SMD inductor. This is a SMD inductor. Here we can see this has two pads where it can be contacted, and in between a spiral wire is forming as a SMD inductor. So because of the small size, the inductor value will be less compared to its discrete or its PTH component, but this SMD inductor is very small and we can put it on the PCB and it offers very less parasitic effects. The next is these capacitors. These are SMD capacitors. These capacitors are also available in SMD form factor. Here the middle point, which is this black color thing, this is a ceramic component which is offering some certain capacitance, and on both the sides we have these connecting pads. These pads are used to connect this capacitor together with the PCB. So they are very small size compared to PTH counterparts, and they offer very less parasitics and go for very high speeds. So nowadays we use all these SMD components to make all our circuits. Now we see, let's say, some surface mount or through hole packages which we generally use in industry now. So we can see certain through hole So in this figure we can see these are the packages which are available for active components. So here inside this we have active circuit, for example, made with MOS transistors and everything. These packages are also available in both the form factors. One is the through hole and one is the surface mount. Here we can see some packages, for example, here the pins are coming out. So it means these pins need to be, first we need to drill a hole in the PCB, and then these pins will go into those holes and then we solder it. The other thing is, for example, this is a BGA package, the ball grid array. These balls are there. These need not to have through a hole. We put this BGA package on the PCB upside down, and then we heat up the whole assemblies. These balls melts out and then make the connection with the PCB. So in this way, this is a SMD components. However, this chip PGA, this is a through hole package. So these are the mix type of ICs available in the market, and we need to choose based on our system requirements. What are actual system requirements? We can choose any one of the mounting technology. So this is all for today. Thank you.